Hi, so I'm presenting this package I wrote called Idealstan, and the first stable version just got released actually to my GitHub page. And because I have a short time, I'm going to primarily talk about the intuition behind this model. It's a model that was primarily developed and used in political science. So, if you're wondering what do political scientists really do, well, when we're not defending democracy from threats, both foreign and domestic, we're building like really cool latent variable models. But I think this has a lot of application outside our discipline, so I'm going to try to pitch it to you. The paper has a lot more of the math behind it. So again, this is a latent variable model, and you've been hearing tons about this so far. You have an unobserved quantity that you want to know about, and your data tells you something about the latent variable. The data are essentially indicators that have some relationship to the latent variable. But the reason it's a latent variable is because the uncertainty never goes away. We never are able to observe what this latent concept is. And these models are really popular in social science, primarily because our data really sucks. So they go by many names. I think the best synonym is measurement models, but these are all kind of different versions of the same theme. You can even use the missing data thing if that's what you're into. And I leave it as an exercise to the reader that the number of terms, the upper bound of the number of terms is equal to the number of statisticians seeking tenure plus 1. So it gets confusing with the terminology. So I define an ideal point model as a hierarchical style latent variable model. And I'm abusing the word hierarchical because I'm not talking about multi-level stuff or hyperpriors. Instead, what I'm talking about is how do we think about the rows and columns in the matrix that we're using that has the data, the observable indicators. And ideal point models are similar to item response theory models in that they don't treat the rows and the columns the same. Matrices don't have to be symmetric, and if you transpose that matrix, you're going to get a different result. So in item response theory language, which I'm going to use for this talk, the columns are items and the rows are people. This comes out of the original application to educational testing. You have people who are answering items or questions on a test, and the latent variable is ability, so how good a test taker you are. And if you do better on the observed indicators, you're a better test taker. The items are used to discriminate between different people who are taking the test or along the latent scale. And the IRT and an ideal point model differ primarily in how they're going to use the items to differentiate between people. And the difference can be kind of abstract. I'm going to try to make it really clear. But in an IRT model, as the observable indicators increase, so as you do better on the test questions, the latent variable, your ability, also increases. In an ideal point model, it could be the opposite. It could be as the observable indicators increase, the latent variable actually decreases. It's going to be conditional on each item or each column in the matrix. So that's the kind of abstract explanation. This is a graph that kind of illustrates the canonical ideal point model. So it's from political science. So pretend we're in the US Senate and we're not screaming at each other. We're listening to a talk. But so right here is the ideal point distribution. Okay, this is the latent variable that we want to estimate. We'll say that the negative values of the ideal points, that's more conservative. And the positive values are more liberal. And we have one senator here, XI. We'll give her a Gaussian to symbolize that we're somewhat uncertain about her true ideal point, but we know that she's fairly liberal, okay? And the senators have to vote on policy. So we present a policy to the Senate. We'll say this is a spending bill, and it's a liberal spending bill, all right? And every bill is going to have a yes point and a no point in this latent space, right? And we know it's a liberal bill because the yes point is over here on the positive values, which are more liberal, and the no point is over here in the conservative values. And so XI here, she's going to vote for this policy because yes is closer to her ideal point than no. But here's the thing. Let's say there's a conservative spending bill that comes to the Senate. It's lowering levels of government revenue. And what will happen is we have to be able to switch that yes and the no point. So if you vote yes on the conservative bill, the latent variable, has to move in the negative direction because that's actually signaling that you're conservative. So we have to change the way that the observable indicators are related to the latent variable. But at the same time, these models are really similar. And actually, in my package, I use the IRT version, the IRT equation to model it. So that's this is the only math I'm going to do today. But this is your IRT equation. You have discrimination parameters for every column. Those are going to tell you how well certain items discriminate between people. You're going to have xi, the ideal points. That's the latent variable. That's all the rows get their own ideal point, every person in the model. And you have the beta j's, or difficulties. They're going to tell you how well someone's going to do on average for a certain item, a certain column. Now, the difference between ideal point and IRT is actually comes down to this one difference. The alpha j's in an ideal point model can take any value in the reals. They can be negative or positive. In an IRT model, a true IRT model, the alpha j's are constrained to be positive. And that's the actual difference. And so it seems really small, but it has a really big implication. What it means is that if in an ideal point model, every item, the polarity of the discrimination can switch back and forth. It could be positive, it could be negative. Think of it like factor loadings. It could load on either side of the scale. And what that does, unconstraining the alpha j's allows us to back out this line of indifference. So if you divide the difficulty by the discrimination, you get the point at which someone would be indifferent to voting or whatever, or responding to this item. So you remember we have a yes point and a no point in the model. In this version, we can't get the yes and the no point, but we can get the difference, the point at which someone is indifferent, and that's enough to be able to estimate the model. Of course, this model is not identified like many latent variable models, and depending on your background, that's like more or less of a problem. I think that Bayesian models do really, really well with these identification challenges because we can constrain priors. We're not just stuck with the likelihood, and that's going to make things work a lot smoother. You can do all this stuff in maximum likelihood as well, and there are packages, great R packages that do this, but the solutions tend to be ad hoc because once you have these latent variable models, you can't use a standard maximum likelihood estimations. You have to use, things like marginal maximum likelihood, a form of expectation maximization. And one of the problems is that you have to design a different one for every model, and you may not get uncertainty or standard errors for all your parameters. In a Bayesian model, the uncertainty propagates through, so we can design arbitrarily complex IRT or ideal point models and get uncertainty in all of our parameters. That's a really great feature. Thank you, Batman. So that's what Idealstan does. Currently, it implements ideal point models for binary and ordinal outcomes. It's really easy to add different distributed variables because, in Stan, that's really easy. It also comes with missing data inference built in. So this is sort of my own project that I wanted to add missing data to ideal point models. It's a certain parametric form that you can read about in the paper. It also comes with a lot of plotting functions because what we want to know are the ideal point distributions, and so a lot of plotting functions so you can see how that works. Also includes the predictive posterior checks for all the models. So the Bayesian data analysis people will invite you to their birthday, and also LUCV. So it includes the ability to calculate leave one out cross-validation estimates with the LU package. And finally, I used some tricks with the variational and Bayesian inference part of Stan so that it actually can automatically identify a model. You don't have to tell it which parameters to constrain, and that's just to make things really easy to use. So the example I'm going to do today is not actually from political science because some people love politics, some people hate it. So I decided to go with coffee because we all love this, hopefully. And I pulled out a data set from these Amazon food reviews, and it has Amazon, every rating has a 5 stars, right? So it's an ordinal outcome. And I pulled out a big data set that someone compiled. And then I just used a regular expression to select those products that mention coffee. So these are really coffee-related products. From that, you can get this big matrix, about 11,000 different raters, or people who have rated at least 3 products in this set. And you have 429 columns. These are one column for every product, okay? So persons and items. That's what we're going to get out of this. And what this model essentially is going to do, it's going to tell us which coffees are actually the most polarizing, meaning which coffees are the ones that sort of people tend to really disagree about. Because that latent variable, it'll depend on which item. People are going to respond to the items differently. And I understand, if you have very strong feelings about coffee, just a trigger warning, I don't want anyone to get too offended because it turns out this guy here is actually, from my model, one of the most polarizing coffees. This is Starbucks Instant Via. My prior intuition before I ran this model, I didn't pre-register it, so Andrew Gelman won't like that, but I thought like Starbucks was going to be pretty polarizing, but then after I ran the model, I was like, oh yeah, of course, Starbucks Via, like the instant coffee, that's what people like really butt heads about. So the way you can visualize this in the model, so this is the ideal point distribution of people who rated Starbucks Via. And the points are colored by their actual rating. So you have 1 to 5. And then these lines here, remember I talked about the lines of indifference? Those are the lines of indifference between the different categories. And what you can see here is that within those categories, it almost perfectly discriminates. So, between the 2 and the 3, everyone's voting 2. And what this is telling you, this really nice kind of within symmetry, is that this Starbucks coffee is able to divide people perfectly into groups. And that's telling you it's discriminating really well on some kind of latent variable, some kind of latent spectrum on which, on one side you have people who like Starbucks Via, and on the other side you have people who just really hate it, okay? So looking at the positive side, which is what Starbucks loaded on, these are some of the other coffees that are really really polarizing. The one at the top is actually Kicking Horse Coffee 454 Horsepower Dark Whole Bean. Look this up on Amazon. It's kind of interesting. Apparently it's like really, really strong coffee, and so some people love it and some people hate it. So these models are cool because they produce a ton of information about your data. And if you're in marketing, maybe you should use this. I don't know. Because you get like all these estimates and you can compare different products. It's really fun. So just briefly, as I said, it also includes missing data inference. And that's a big problem with this data set because most raters aren't going to review every product on Amazon. People don't go on and just like review product to product to product. And so what my package does is it assumes that missing data is a function of people's ideal points. So if you're only going to review products that you really like that are close to your ideal point, you're going to opt into rating them. All right, so it's like a censoring or a hurdle model. And that allows us to include all the data in the model. And so on the right-hand side, this is the ideal point distribution for all of the data, including missing data. And you can see that when we include missing data, unsurprisingly, there's actually a lot more discrimination, a lot more spread in that ideal point distribution. And this is built into the package. You can just essentially hit a button and it'll change the model. And again, I think that's the beauty of Stan, that we can incorporate new features into existing models really, really easily and using the same programming language. So what's up next? I said the first stable version's on GitHub. I'm hoping to get it through CRAN soon. It currently actually already has the ability to like latent regression and also time series priors on parameters. It's just not documented yet, but hopefully I'll do that soon. I need to add in marginal lieu, as I learned yesterday. Marginal lieu is really important for IRT. Like, okay, I got to do that. And then I'm also interested in exploring more how to best identify these models. And also, I'm just interested in adding like new IRT and ideal point models. There's a lot of models in the literature that were kind of like a one-off model, and no one uses them because they're really hard to code or set up. So I'm hoping to add on more models in the future. So thanks.
Okay, questions? Yes.
I'm just curious about the scale that these models are running at, like when you're doing these product models, how many users, how many products, how long does it take to run?
I mean, I haven't really tried to time it because obviously it's going to depend on the number of columns, the number of rows in every single matrix. I mean, it's going to, you get like to the size of like this coffee database. So I was using variational inference, the VB built into Stan to do this, just to make it simple. And that's kind of my recommendation, like run it in VB first just to get a sense of what it looks like. But that model probably take like a few hours to run would be my understanding. I coded it, so if you're familiar with Idealstan package, which is a phenomenal package, it's coded very similarly using ragged arrays in Stan that tries to make it run faster. I can't fully make it run super, super fast because the code has to be kind of general to allow for different options. So I won't say that's like the most optimized code, but it's not bad.
Another question over here.
Hi, thank you for the talk. I have a question about, so in this Amazon data, you basically had probably a situation when your contributors are basically participating in just one item, right? And most of contributors, they do not participate in several items. And in most of ideal point model, you need to compare. So you need just this cross sampling between different items, which are connected by different people in educational environment. So I guess you're lucky with Amazon data because the scale is the same. It's from 1 stars to 5 stars, so it's easy to calculate what is sparse. But how would you deal with the situation when you have separated data? So let's say you have 2 subgroups of students which answer to different items, or you have 2 subgroups of some people answering different political questions, but in different, surveys.
Mm-hmm. Yeah. So there's 2 things. So one, if you have if your outcome variable, you have like different outcomes over time, like you have some like binary and some ordinal. That's really easy to do in Stan because it's just a joint model. Essentially, you just like add that as an outcome. I don't currently implement that, but it's fairly easy to code in Stan. If you have things like you're worried about kind of item heterogeneity, you have some items that have you think it's leaving stuff out. That's what the latent regression is for. So you can include a covariate that codes the items differently, maybe by time period or a test effect or anything really that you want, and that'll essentially account for that variation in how the items are functioning in the model. So that's kind of the most straightforward way is to include extra covariates that, like a multi-level model, they're at the item level covariates.
Other questions? If not, I have a question. Do you plan or currently support multi-dimensional ideal points?
Yeah, that's one thing that I have not added in yet, and that's another thing that's really, really easy to do in Stan, which is so nice. And I just have to write a new code file and add that as an option. It has to. You want to keep the multi-dimensional thing separate because that's really going to slow things down, just the way you have to code it. Because you have to have some like giant matrix for all the different dimensions. But yeah, that's another thing that I'm going to do soon. It'll be multidimensional. It'll be like a compensatory IRT model if you're familiar with those. Yeah.
Okay, so let's thank Robert.